Hello everyone, and welcome to the conclusion of the statistics overview. We'll talk about chapter 4, linear models. So a linear model is a particular type of statistical model that tries to describe a relationship between an input variable x and an output variable y that are both continuous. So you can think of a line, the equivalent of a line, mx plus b, but now we're talking about random variables. So here is the expression mx plus b, but instead we're going to use the letters beta 1 for the slope and beta 0 for the y-intercept. So the context to analyze here, so this relation between two numeric variables, the input or the independent variable and the dependent, the output variable. So we can talk about the relationship, how does y depend on x by the end of this. So why we need linear models in the example of the statistical training improving employee lifetime value is, in that context, we're going to analyze the following situation. Previously, in the previous videos, we had off or on. So either you did 100 hours of statistic or no statistics at all. But now we have new data set where we have variable amount of statistics. So it's measured in hours, and it's somewhere between 0 and 100. So we know what happens when you have 100 hours, but we want to know what happens if you do just 30 hours of training and so on. And what we're going to try to build is a model of how the employee lifetime value depends on the number of hours of statistical training. Okay. To build this model, to estimate these parameters, Amy has collected new data. Okay, so here is the new spreadsheet. For each employee, now each row represents an employee, measures how many hours of statistical training they completed. So you see some people completed almost 100 hours, and some people very little, just 4. And so she has the number of hours of training and the employee lifetime value after 1 year. So similar to before, but instead of being 100 and 0, we have two groups. We have a continuous number of hours. So let's take a look at that, the data frame. So it's as you see in the Excel file. Okay, so we'll get started, but the purpose of the model here is to understand this relationship. How does the employee lifetime value depend on the number of hours? So we'll talk about that in a second, but first let's do the data part where we just get the statistics. So the number of hours, so there are 33 roles, 33 employees. The average number of hours is 57, 58 almost, and the average employee lifetime value is 1,000. So this is somewhere in between what we saw before. Let's look at the data. So the scatter plot is a good plot for this because we just have points. Horizontal axis being the number of hours, and y being the employee lifetime value. And if you squint the right way, you will see there's as the number of hours grows, the employee lifetime value grows. These points don't really fit the line, but there seems to be some sort of line going up. Okay, so spoiler, you can Seaborn can fit the linear model for you and plot it in by calling this one command. And so this is what the best linear model looks like. So the name should tell you linear model means looks like a line. So the intercept is somewhere here, and you see it passes through the points. Doesn't pass through all the points, but it's the best fit. So we're going to work our way to this plot, but I wanted to show what we're trying. So we're trying to understand these points. We're going to try to fit to the best fit line. Okay, important that this is a linear model. Okay, so we're looking for a linear relationship where the change in employee lifetime value is proportional to the change in the training. Here are some other type of models. So this is the one we can we will have here. We can we're talking about, in this notebook, we're talking about linear models. So the input, the output depends on the input. Here are non-linear models. So it's very possible if maybe 25 hours of training is enough and then there's no benefit after that. So this is like early gains. The reality, this is not a model. Imagine a data that behaves like this. Mid gains would be there's no benefits in the beginning, so almost zero slope. All the gains happen after 50 hours and then again it flattens out. Or it could be the opposite. There's no gains at all until 3/4 of so 75 hours, and then suddenly all the gain is unlocked. So these three are non-linear, and if the data behaves, if the relationship between hours and gains is any of these types, it's not a good fit for the linear model. Understand? Like we're trying, the linear model only works well if the relationship is linear. Luckily, many of the phenomena in nature and in data science are of this kind, where increasing one variable tends to causes a linear increase in the other variable. So it's a very general purpose class of linear models, but it doesn't mean there are other data relationships that it will not work. So just a caveat. Okay, so this is what the plan for this video is. We're going to learn how to fit linear models, much shorter than the other videos, and how we interpret the results of the fit. And this will be it. Will be very quick. Okay, so what does fit mean? So one, it's a method, the method we'll use. But fitting means to find the best parameters beta 0 and beta 1 that make a line to create the line that best fits here. So the y-intercept and the slope. So if we try a different line, it will be further from these points. If we try a line like this, it will be further from these points. So this line that we see here is the best fit. So stats models, OLS, ordinary least squares, is one way to do this. And here, linear models are so important and so popular that there are at least 5 other ways accessible in Python in standard libraries for fitting models. So we're not going to talk about all of them, but just to let you know that we're showing 1/6 of all the possible ways. Okay, so let's do it. The stat models has something called a formula API, which allows you to input the model you're trying to fit directly as an expression. So in this case, the expression we want is 1 plus hours. Let me show you where it will use it. We put in a string in quotes, EOV is proportional to 1 plus hours. So really, essentially, in front of each of these expressions is the coefficient. So beta 1 and beta 0 for the 1. So it's not exactly like the math formula because the betas are implicit. So we don't need to give this a name, beta 0 and beta 1. The model knows that there is implicitly behind the constant 1, there is some coefficient, and behind the hours, there's another coefficient. So as you see in a second what happens. So this is everything we needed to do, is use the variable names. Let's go back to the data. Head just prints the top few entries. Oh, we can print the whole thing. Okay, now let's print the... So you see there's a column called hours and a column called EOV. So in the expression for the model, we're using the same variable name. So it's not like I invented these. These are already in the data frame too. So that is it. You say, build me this model. Okay, and it gives you an object called, it's a type of stats model. And then you call the model fit. So fitting a model can be thought of as an optimization problem, or it could be done many different ways. But by the end of this, running this cell, result contains the best choices of the parameter beta 0 and beta 1. Okay? And this is the best fit. What do we mean by best? We mean that the distance between the line, can we plot it? Let's plot it. So we have again all the data points, and we have here a line plot for the model, best fit model. So going back to the best fit means that this distance, the error, or the residuals, so each point is not well predicted. This point is very well predicted by the model, but in general, by trying to fit all the points, we had to make compromises. And the distance between the model and the actual point is called the residual. The sum of these residuals, the squared residuals, is the smallest possible. Any other line would increase the squared residuals. So that's what it means by fit. Okay, and it's a convenient way to find this best fit line. But the stats model here, the result contains a lot more information. So get ready for this. Okay, so here is the data we already looked at, the coefficient for the intercept. So the y-intercept is 1005, and the coefficient for the slope, 2.56, so the slope of this line. Not only do we have the coefficients, we have an estimate of the standard deviation of your standard error. We'll talk about those in a second. There's a bunch of other metrics for the model. The R squared, there is information criteria, there's a lot of data. Okay, the degrees of freedom. So in general, the stats model prints a lot of information that we don't need for this case. In this case, we just wanted the parameters. But as you learn more about statistics, all these things will become more important. Okay, so behind this cell, I've hidden a bunch of other ways. So this notion of finding the best parameters, beta 0, beta 1, there are at least 5 other ways to do this. You can use linear algebra, you can use scikit-learn. This is a machine learning library that contains linear models in it. All of these do find exactly the same numbers, the same optimal parameters. So if you're interested, you can unfold this and read about the details from these other options. In the interest of time, I'm going to skip that. Instead, let's talk about the interpretation. So we talked about the coefficients, right? The beta 0 means the x-intercept, the y-intercept, beta 1 is the slope. There's another coefficient called r squared, which we saw it here. This tells you how well the model fits. The proportion of the variation in the dependent variable that is predictable from the independent variable. Okay, we'll talk about that in a second. You can also plot the residuals, which we're not going to do. And there are a bunch of other metrics. So in general, when you choose a model, the model fit to data is there's a lot of metrics to measure. Okay. So let's look at, again, reminder, the summary. We saw that earlier. We saw the parameters. The r squared coefficient is 0.36. This is on a scale from 0 to 1. And we are kind of far away from 1. So we don't have a very good fit. Okay. Another thing we can do directly from this table, we have all this information here, is ask the following question. Usually, I mean, you can ask it for r squared, you can ask it for the slope, you can ask it for the intercept. So let's talk about the slope. Remember what we did with hypothesis testing, where we ask a yes/no question. So we have here a similar yes/no question. Is the slope, so if this model is measure of relation between the hours of statistical training and the increase in EOV, employee lifetime value, then the slope should be non-zero, right? As you increase the hours, you should increase in employee lifetime value. But again, someone could be, a skeptic could say, no. When you change the number of hours, nothing changes. The employee lifetime value is constant. There is no slope. The slope is 0. You increase the hours, the employee lifetime value stays the same. So we can put these two hypotheses to a test, right? So we say the no hypothesis says there is no relation. The line is flat. So the best model describes it by a constant. In other words, the linear model, we don't need a linear model. A constant would be good enough. Or the alternative, which is what we have, is there is a slope here. And the coefficient here is non-zero. So is there a relation, is there a positive relation, well, is there a relation between number of hours of statistical training and improved employee lifetime value? That's how we're going to measure it, is by asking, is the slope 0 or non-zero? And in fact, when you fit the model, it already did this test for us. The p-value is crazy small. So remember that the cutoff for there is a difference is 0.5. So there is a slope. The slope is not 0. We are very, very sure that it's not 0. And not only that, but it also computed a 95% confidence interval for us. So the slope, the hour slope, this gives you a 95% confidence intervals for each variable, and we select the confidence interval for the hours. It's somewhere between 1.3 and 3.8. Remember, the actual value was 2.56. So this is what we can conclude, is that for each hour of statistical training, there is a 2.56 increase in the employee lifetime value. And if someone asks, well, are you sure about this 2.56? You say, well, yeah, actually, it's somewhere between 1.3 and 3.8. So that it's not guarantee of 2.56. This is the confidence interval we can give, which is still pretty good. Even in the worst case, we're still statistical training is helping improve EOV. So the more you do, the better. Okay, let's look at the model again. Okay, these are all the data points we have. Now imagine we have a new employee that, and we ask what happens if we give 50 hours of training, so here, and we don't have a particular employee with this data, but we can predict whatever the model predicts. So the model predicts that for 50 we should get something like 1,150 or something. Yeah, 1,130 employee lifetime. So this is what the model is good for. We can predict the outputs based on, we can predict the Y value, the employee lifetime value for any number of hours, not just the data points we have. And this prediction is the average, right? Every employee will vary, but the best fit line tells us the average of these, like the mean. Similarly, after 100 hours, we get this value here. Note, however, these are called interpolation. So interpolation is when you use a model, it works between here and here, and now you find values in between. Extrapolation is when you ask the model to predict values in a range it's not been designed for. So for example, you could ask what happens, well, we see this trend that the more hours, the better the employee lifetime value. You could say, well, extrapolating to 200 here, what will be, can we predict? So you see, if you plug that into the model, it will predict that the employee lifetime value will be 1,500. But this is not allowed. Don't do that. The model, right, the only data, the model is just a summary of the data. And all the data we have so far is only been tested to 100 hours of statistical training. So asking the model for prediction over here with the 200, we don't know. Maybe it flattens out here. Maybe it drops. Too much statistic is damaging to the psyche of the employee. They decide to quit. Or it could be super linear. It could be really, wow, they hit some threshold and they start to see, like in the matrix, everything, the numbers are, we don't know. We just don't know. So don't try to push the model beyond where it was designed for. Okay, so that's it. I mean, this was a quick intro on a very important topic, but we already saw a lot of other topics, so let's not make it any longer. In the book, we'll talk not just about linear models, but about generalization. So instead of linear relation between an inputs and outputs, we can talk about logistic regression, which is adding a non-linearity. So we can start to model this kind of shapes, and that's very helpful for binary data. So if the outcome is pass or fail, we'll talk about that. I invite you to click on this link and learn about a very interesting result that linear models, what we talked about in chapter 4, actually will give us a chance to review many of the topics like t-test, ANOVA, and other tests in the book, and unifying them as one model, as one framework. In addition, this notion of fitting a model, optimizing, choosing the best parameters is a very important concept in machine learning. So by learning about linear models, it's a pure statistics, it's very like classical statistics, but you're setting up your knowledge and the vocabulary for machine learning. And so the idea of fitting a model to the data and then using the model to predict outputs on new data is pretty much word for word what supervised machine learning does. So we won't do actual machine learning, but the tools you learn from linear models are machine learning ready. So we'll just touch upon certain aspects, but machine learning is a whole other book. So that's it. I'm going to conclude here. The book is coming. This video series was very helpful to organize the ideas and plan. I've got the sample chapters coming up. So if you want to be kept in the loop, here is a mailing list which I will send chapters once every 2-3 weeks, and concept maps, and yeah. For the moment, sign up, and if you want to know more details about the book, the Google Doc contains everything you need to know. Very detailed. 22 pages of outline. Look at that, it won't even load. So many of the topics we covered in this tutorial will be covered in the book. In the outline, you'll see how they will be developed further. And of course, I mentioned the concept map. It's all those little boxes that we looked at during the tutorial. They're part of the overall picture. So take a look now as to see how it all fits together. Okay, that's it. I'll keep you posted. It's coming along nicely. Sorry it's been so many years, but the statistics is not easy, so trying to summarize and find the essential elements has been a challenge, but now we're in a good place. It's coming up. By January there will be a book. Are you ready for it? All right, ciao.